talk about implementing the logic function f as shown here without doing any type of Boolean algebra. All right, so I want to implement it as shown so you can see the logic expression. And what we're going to do here is we're going to use regular gates, the kind that you would just normally think about using, and then we're going to convert each of these regular gates to NAND gates. And I also want to preserve the shape distinctive gate symbols, and I can do that by appropriately placing bubbles so that the original logic function meaning is preserved. So let's get started. Okay, so the first thing I want to do here is highlight a few things that I'm going to start with. I'm going to start with these two AND gates. All right, so these are product terms, and so I can draw gates here. Here's an and then here's also an and. All right, I've got A bar coming in. I've got B coming in. So in the output, I have A bar B, and so that matches with the blue term that I highlighted above. All right, and then on the input down here, I have X bar, so I need an inverter for that. And then I have Y coming in. So that is the red highlighted region in the Boolean expression. So far so good. We have those two terms. And then what I want to do is I want to make this OR term. All right, so I'm going to highlight those together. I've already got the product term, so I just need to OR that together. All right, and so I highlighted that with yellow, so let's go ahead and do that. All right, and so coming out here, I have X bar Y, and then I also need C bar. To get the C bar, I need an inverter for C. All right, so this is the term that I wanted, C bar or X bar Y. Nice. All right, and then I need to AND both those together. So we're ANDing this whole expression together. These two terms have already been formed. And so what we're going to do is have an AND here. All right, we're going to go and AND these two terms together, and that gives us our logic function f. All right, so I'll highlight that in green because it was the product term that I circled before in the expression. All right, so this is our original circuit. All right, that's done with just the logic gates as you would normally think of the logic gates as written. All right, so what I want to do now is use essentially DeMorgan's by using bubbles in appropriate places to implement this with only NAND gates and inverters. Okay, so my first step is to convert the ANDs to NANDs. All right, so I'm going to redraw all the NANDs that I see with bubbles on the output. Okay, so I think of it as I want the AND function, but I want to implement it with an AND gate. How do I take that function? So I take the AND distinctive shape, put a bubble at the end, and I get a NAND gate. All right, similarly for OR. All right, we had talked about, if you take an AND shape and you push this bubble back through, it turns the shape into OR and puts the bubbles on the input side. All right, so this is a NAND gate, but I have the shape distinctive symbol preserved. All right, so I still can tell that that's supposed to take the OR function. If I put the bubbles there, it still preserves that. And so I've got all the gates set up. All right, so let me highlight the different terms. All right, so here's that blue gate turned into NAND. Here's the red turned into NAND. Here's the OR gate turned into NAND, and the last output also turned into NAND. So we have all NAND gates at this point, And now we just have to use what we know about the original logic function in the input terms to match everything up to get the final output. Okay, so I'm thinking here, I still need a bar. There's no bubbles on the input, so nothing changes. And I still need B, I forgot to label that here. I need X bar, and I need Y. I need C bar. Now, notice what I get from C bar. I can take C straight to the bubble, and on the other side of the bubble, it comes out, other side of the, because it hit that bubble, it's C bar on the output, and this is an ORing, because it's an OR gate. All right, so I'm going to take this function, or this output, and those two bubbles will cancel, and so what I know is that this shows up as X bar Y on the output. All right. So from here, I can move this. There's no bubble here, so I don't have to match anything. But on this side, I've got a bubble on the output that I need to cancel before I take it to this input. All right, so I'm just matching the bubbles, adding inverters when I need to, interpreting what a bubble would be on an input side. All these things are relatively straightforward. All right, on the output though, I have a bubble, and I'd like to not have a bubble and just use F by itself without it being inverted. Okay, so this is the full circuit. I started with the usual method for implementing a logic diagram with AND gates and OR gates and inverters, and now this is all NAND. Notice I preserved the shape distinctive symbols, and so the original meaning of the logic function is preserved. All right, so the next thing I want to do is compare transistor counts so that you can see why we would care about doing something like this. All right, so to do that, let me clean up the screen a little bit. All right, let's think about what we have in terms of gates. So I'm looking at the top diagram, and I see 4 gates that have 2 inputs, and they're either AND or OR. Now, in a previous section, we talked about how these gates with AND and OR are actually formed from NAND and NOR. So you have the NAND followed by an inverter. So that would have 4 transistors on the NAND part, and then another 2 transistors for the inversion. So that's 6 transistors for each of these. So I have 4 times 6, so there's 24 transistors for the gates themselves. Okay, and then I'm looking at how many inverters do I have. I see 3 inverters, and each of those is 2 transistors, so that's 6. So it looks like we have a total of 30 transistors in this top implementation. Okay, so down here on the All-NAND, what I see is 4 NAND gates, and each of those takes 4 transistors, so 4 times 4, we now have 16. That's where the savings comes. All right, but it does turn out that we had to have an extra inverter to make this all work out. So that's 4 times 2 transistors for each inversion, so 8. But we do see a savings of 6 transistors if you implement things this way. Okay, so I like to think of this in levels of abstraction. When you have a Boolean function like we have in this example, what I'm thinking of is, this is my natural instinct of how you would implement this. But when I look at this circuit, in my mind, I know that it can be converted to all NANDs, and you could implement that more efficiently. I don't necessarily need to do that unless I care about it at that particular level. So normally we work up here with this circuit, but then in the back of our mind, we're thinking, this could actually be implemented more efficiently with fewer transistors if we move to this implementation. But I don't necessarily have to show that everywhere, but it's good to know how that works so that I can keep that in mind. In the second example, I want to repeat the example I just did with example 1, where I implement this logic function using all NOR gates and inverters. So the process is the same. I'm going to start with the original Boolean function laid out like we would normally do with regular AND gates and OR gates and inverters. All right, so that's the same starting point as example 1. The difference is that now I'm going to push the NOR gate. All right, so here's the NOR gate. If I push that bubble backwards, it changes the shape, okay, but preserves the gate. All right, so this is a NOR gate. That's obvious. This is also a NOR gate. All right, so we're going to convert all the ANDs to NORs. Okay, so I don't need this anymore. Let's get rid of it. So the first thing I do here is I draw all the NORs. Here's a NOR. Here's a NOR. Here's a NOR. All right, so that takes care of the blue AND gate, the red AND gate, and the green AND gate. Then I have the yellow OR. All right, that's pretty easy to convert because OR with NOR is a bubble on the output. All right, so I have these set up and ready to go. I just need to match bubbles, okay? All right, so what I'm thinking here is I need a bar showing up in the output. I have the bubble already on the input side, so that helps me generate a bar. But for B, I need B showing up on the output, and so I would need to cancel that bubble for it to show up on the output. Okay, similarly for X, I have X bar showing up on the output. I need to invert Y so that the bubbles cancel, so that Y shows up on the output. Okay, so here we go. And then I need C bar. Well, there's no bubble on the input of this NOR gate, so I need to actually form that inversion. Okay. So there we go with C. So that takes care of that. I noticed I colored the gate wrong. So let's get that back to yellow. Okay. And at top, these bubbles match, so I can go straight to here, but I need an inversion here to cancel the bubble on the input side of this Boolean function. All right, so that completes the work. I now have this completely implemented. This is an all NOR and inverter implementation. Okay, now let's do the transistor count. All right, it's the same type of thing where I'm counting 1, 2, 3, 4 NOR gates, and each of those takes 4 transistors. Okay, and then I'm counting 1, 2, 3, 4 inverters. So it's not a surprise. It's the same as the All-NAND. So what I have is two transistors per inverter. So I'm 16 plus 8, which is 24 transistors for the all NOR implementation. So this duality is not a surprise. You would expect basically the same answer with an all NOR as you get with all NAND. But the point is that by using these universal gates that come from DeMorgans, you can implement circuits more efficiently. Here's another example of this process of converting a logic function to an all NAND and inverter implementation. So we talked about using universal gates, using DeMorgans, to come up with more efficient circuit implementations. So let's do this again as an example. And what I wanted to do first is I've already got this laid out in terms of just AND gates and OR gates, but I want to make sure that you understand the thought process on this. So for me, the thought process is to look at the Boolean algebra and form things according to the precedents in Boolean algebra. So I'm thinking here, here's this product term. All right, so the first thing I do is I check, here's the product term, and down here, here's the product term. So I need to form that as one of the first things before I get to the OR. All right, so once I'm there, I can then OR those two terms together to get this term shows up here. Okay, the next thing I did was I looked at the ORing of this term. Okay, so this blue gate here becomes this term right here. All right, from there, I just AND those two things together to get the overall Boolean expression where I AND those together. All right, so hopefully you're realizing that the Boolean algebra hierarchy matters, and you can look at that and use that to decide how to lay out the initial layout of your circuit. Okay, so from there, it's just a matter of converting to NANDs. And so we're going to do that quickly so this video is not very long. An AND gate is just converted to NAND by adding a bubble on the output. ORs are converted to NAND by putting bubbles on the input. And there we go. We have all of our gates converted to NAND. So now it's just a matter of matching up the signals. All right, this has B bar. This has C. D, we can use the bubble. So when I hit the bubble, D bar shows up on the output. E needs a canceling of the bubble because it should show up uninverted on the output. Okay. And we notice the path then goes to here for the lower OR gate. All right, this bubble cancels with this, so it can go straight in. And then I need A coming in, so I need an inverter here. Okay, no inverter needed here because the input doesn't have an inverter. And then the output needs to be inverted to get to G. All right, so there's that expression. So if we did the transistor count, all right, what I'm looking at on the first circuit is 1, 2, 3, 4 and OR gates. These each have 2 inputs, and so 6 transistors each, so 4 times 6. All right, and then there's 2 inverters. Each of those has 2 transistors. 2 times 2 is 4. So we're looking at 28 total transistors for the AND OR implementation. So down here, I'm seeing 4 NAND gates and 1, 2, 3, 4 transistors. So 4 times 4 is 16. Remember, the savings comes from not needing that extra level of inversion to go from NAND to AND. All right, so there's 16 for the main gates, and then I count the inverters. 1, 2, 3, 4 inverters. 4 times 2 is 8, so 24 transistors. So a slightly more efficient implementation if you do all NANDs. Final 4th example, what we're going to look at here is converting the same logic expression from example 3 to all NOR gates and inverters. Okay, so we've already established, here's the initial circuit with ANDs and ORs. Let's convert all the gates to NORs. All right, so I know for the AND, what I need is bubbles on the input. Okay, for the OR, what I need is a bubble on the output. So basically it's the same layout, but now I have the gates converted to all NORs. All right, so for the input B, I hit the bubble and I get B bar showing up on the output. For C, I need to cancel that bubble so that C shows up on the output. All right, so B and C here. And then for D, there's no bubbles on the input, so it's just like before. Okay, and then I need this output to go here. The bubbles already cancel. All right, this input goes here, and I have A showing up here. The bubbles already cancel. Okay, and so this particular implementation works out really well for all NOR. Okay, so let's do the transistor count. What I'm seeing is 1, 2, 3, 4 NOR gates. So that's 16 transistors, 4 times 4. And then I count the inverters. 1, 2, only 2 inverters. Okay, so a lot of times when you see products, the NOR gates work better with products. And if you see a bunch of sum of products, product of sums is what I should have said. Notice this looks like product of sums. And so what we're seeing here is 16 plus 2 times 8, 2 times 4. 2 times 2. There's 2 inverters. So it's down to 20 transistors to implement this with all NOR gates.